Good afternoon, everyone. So, first of all, I thank the organizers to giving me an opportunity, and of course, it is a privilege for me to share the dais with eminent from the industries, from the downstream industry particularly. So, I am going to here present technology which BPCL R&D has developed, and this technology can save energy for three-phase processes where we are having high pressure requirements like hydroprocessing, hydrocracking, hydrotreating, as sir also mentioned. So it is the product which we can have during that energy transition period. So that was the most relevant to this session. So let me take you through the technology development journey. Yeah. So yeah, it's okay. Yeah. So typically there are trickle bed reactors which are being used in refinery. So I think most of the audience may be knowing it, but maybe I see that there are few students. So trickle bed reactors are fixed bed reactors which are having a solid catalyst bed as a fixed bed, and then there are gas and liquid flowing through the bed from top to bottom, and their reaction is taking place on the catalytic particles on the surface of the catalyst. So, and we get the products, and the typical reactions which are being carried out in refineries are hydroprocessing, where we are treating the sour fuels like diesel or VGO or gasoline also nowadays. And they are also used as for treating, where we are converting a very low value feedstock to a high value of like diesel and all. So these are having some bottlenecks, these reactors. So basically, when these reactors are using very high gas to oil ratio, so the volume of gas is being fed up to 1,000 times of the liquid volume. So basically, that leads to vaporization of the liquid feed, and these reactions are liquid feed reactions. So the moment the liquid gets vaporized, there volume for the reaction will gets reduced, and as we are having high temperatures also, they are ranging from 350 to 450. So the temperature and pressures there, and more volume of the gas, the vaporization increases, and that also, because of that, since we have more vapors, there will be reducing the partial pressures of hydrogen. So this will reduce the solubility of the hydrogen in the feed, and of course, since there are more vapors, it will also have more pressure drops. And there are also secondary reactions taking place because all the products are going from top to bottom. So all the lighters will stay in the bed, and then the further reactions will take place to go towards the gas formations. So moreover, there is also all the products will stay in the bed, so that will lead to product inhibition. So the reactions there will slow down the reaction rates. So there are papers which are discussing, the literature is discussing about having interbed separators, where we take the products from one bed, because there are multiple beds for temperature control. They are in between quenches. So they take products from each bed, and then separate gas and liquid, and only liquid will go to the subsequent bed and gas will be separated. So this has proven to be improve the convergence in the process. So as the more number of interbed separators, better the conversion was. So we thought of, why don't we have an infinite number of GL separators. So that's where they introduced the concept of cross flow reactor. So in this, basically the liquid flows same as the trickle bed reactor from top to bottom, and we introduce the gas from through a central distributor and the radial flow, as we are having in CCR reactors. So the gas will be flowing radially from center to outward, and the liquid will from top to bottom. So this process will definitely reduce the pressure, because the gas is traveling very short way. Instead of length, it is traveling just a few meters, like 3 to 4 meters only maximum, and not even 3-4 meters, 1 to 2 meters, because the diameter is 4 meter roughly. So the pressure drop is roughly 25% of the existing bed. Since the gas is leaving the bed, there is no competition for because there is a void volume in the bed which is there for gas and liquid both. So now the gas is leaving, so there is more place for the liquid, so there will be more liquid hold up, so more liquid volume inside the bed. So, and this process is going to save energy up to 15% in the in case of TBR. And since there is a low amount of gas seeing in each length, so the vaporization is reduced significantly, and since the product gases are also leaving the bed immediately they are formed, so there will be no inhibition, so we have more reaction rates. So with this, we also got a patent, US patent granted on this technology, and there are more patents filed which are there already in the process. So this process can be applied to all the applications where three-phase reactions are taking place, like lube oil base stock production, hydroprocessing, as I mentioned, resid upgradation, or nowadays we are focusing on bio-ATF formula production. So there also we can apply this technology. So let me take you the journey of the CFR development. So first, as we did the more stimulation studies, we conceptualized the process, and then we made small prototype models in the acrylic setup starting from 10 centimeter diameter. So that's where we studied the hydrodynamics of the system, whether the system is feasible or not. So we compared all the liquid hold-up, pressure drops, and then we saw that that's how this is going to work. So based on that, we now, since we know that since the gas and liquid will flow in the cross direction, so there are inherent challenges which will be there in the process, because the gas will be pushing the liquid away. So those so that there will be dry zones and all those issues. So we take the challenge to design novel internals which can optimize the catalyst wetting inside the reactor. We can have a more uniform gas and liquid distribution. So for that we have done extensive simulation studies and also designed novel internals, and we proved that those internals are going to work on those conditions also. We have tested with the real gas and liquid conditions of diesel, DSDT, VGSDT and all. So based on that studies, we set up a small 100 TPD almost capacity plant in our R&D center. That is only for cold flow study, so we are only using air and water system. This plant is just to show that all the internals which we have conceptualized and we have simulated in our system, they are going to work fine. So what we did, we installed those internals on the plant, and we did a study, RTD study. So basically it's a residence time distribution studies which will tell you how the liquid distribution is there within the bed, because since this being a SS reactor we can't see inside it. So we can have radio tracer studies which we did through BARC, where the inject the radio tracer at the start of the reactor and monitor the radioactive particle activity at the end of the reactor. So that's where, based on the analysis of the data, they will tell how the distribution of the liquid is there within the bed across the length. So we have confirmed that in the typical hydroprocessing conditions which we have in the refinery, at those conditions the internals will ensure that there is a uniform distribution of the liquid, and the hold-up of the liquid is higher than the TBR, which we have compared from the typical trickle bed reactors. So based on those studies, we have proposed a 120T VGSDT plant at KR, which I think few of our colleagues also there who are part of this discussions. And the proposal is under discussion with the top management, where we are planning to put this plant in for VGO hydroprocessing. So there will be basically mild cracking and mostly treating of the VGO feed. So we have made all the calculations based on this. So we have developed a basic engineering design package, where all the HAZOP and HAZIT studies has been completed. So we also done a few case studies with the refinery units, which will demonstrate the energy saving. So here we see that there are three profiles. One is with the zigzag here. These are because of the temperature profiles, because of the quench. So now I forgot to mention one thing, that in CFR reactor we don't need a quench, because since the gas is throughout the length, there is no extra quench required for that. So the cooling will be done through the gas, so the same gas only. So that's why we maintain the temperature profile across the reactor also. And since there is a gas separately we are sending, we can heat the gas at the lower temperature, so that will save a significant amount of energy. The second case study which we did for hydrocracking unit for Mumbai refinery, so where we tried to simulate the process, we can see that the same conversion of TBR can be obtained at a lower pressure. I didn't show the number here because we are submitting a paper on based on this, so we have just to keep the secrecy as of now. And but it shows that we can have the same conversion of TBR in CFR at the lower pressure. So that is again in terms of we are saving energy. So in the last, to conclude, basically we have this indigenous technology demonstration which we can which can be a contribution towards Make in India campaign, and it's first of a kind because the 3-phase in a cross-flow manner is nowhere used in the world as on date. And of course, as I mentioned, all those profiles that shows that there is a significant energy saving in the hydroprocessing applications. So we are identifying a partner to technology partner along with which we can collaborate, and we can further commercialize, because the plant which I was discussing of refinery 120 tons per day, it is a demonstration plant which will demonstrate the technology, and we are planning to partner with a technology partner to further scale it up to a commercial scale. So the current proposal is to have a parallel unit to hydroprocessing unit, so that we can demonstrate it in terms of product quality and other benefits which we are seen through the simulations. So that's all. For further information, we can you can go through the link. That's all. Thank you.
Is it a lab scale or is it a pilot plant?
Sir, for hydrodynamic studies, we have gone up to 100 tons per day scale.
Achha.
For hydrodynamics, because the plant I shown, it is in the R&D center we have. I am personally operating that plant. So up to 100 tons per day, it is 3 tons catalyst capacity it can house it, and we are operating in cold flow conditions.
Good.
And we are proposing a hot unit for real feed conditions in Kochi refinery, and the discussions
And you are
are
going for scaling up now.
Yes, sir.
Congratulations. Very good.
Thank you, sir.
So it's a very innovative technology. Thank you very much for giving introduction to that.
Thank you.
I am sure there will be a lot of energy saving, and from there other refineries will also try to adopt this technology. So thank you very much. I think we are very much on time. Thank you all the speakers. And just to brief that in this session, we have gone through how the development is taking place, how we are trying to reach the zero emission by 2070, taking small steps everywhere in all the refineries, all the operations, and developing new technologies, going for integration approach. So all these things will definitely help our country to achieve the target set up by Honorable Prime Minister in COP26. Thank you very much for your attendance. Thank you.
Thank you very much, sir. I now request Mr. Anil Razdan to please join us on stage for memento presentation. Mr. Anil Razdan, former Secretary Power, Government of India, Chairman, Energy and Environment Foundation. I now request sir to please present a token of appreciation to Chairperson Mr. Brij Mohan Bansal, former Chairman, Indian Oil Corporation Limited. A round of applause, ladies and gentlemen, for Session Chair Mr. Brij Mohan Bansal. Thank you very much, sir. Mr. Biswa Bhushan Mohanty, Head Maintenance, Dhamra LNG Terminal Private Limited. Thank you very much, sir. Mr. Satya Narayanan, DGM Bharat Petroleum Corporation Limited. Thank you very much, sir. Mr. Sridhar K, General Manager, Digital Kochi Refinery, Bharat Petroleum Corporation Limited. Thank you. Ms. Priyanka Dogra, Assistant Executive Engineer, IOGPT ONGC. Thank you very much, ma'am. Mr. Vinod Kumar, Manager R&D, Corporate R&D Center, Bharat Petroleum Corporation Limited. I now request all the panelists to please come forward for a group photograph.
This was a B-dominated panel.
Yes.
Right from Mr. Bansal to Bharat.
Yes.
The lady, she was an exception, I think.
ONGC, yes. Yes, majority were from Bharat Petroleum. Please give it up for all the speakers, all the distinguished panelists. Thank you very much. Ladies and gentlemen, we'll take a short 10 minutes tea break. As we are running behind schedule, we request you to please join us at sharp 4:15 p.m. for the last session of the day. The tea is organized outside this hall. Please make it quick. Thank you.